it's going to be given by Mehtaab, and he's going to talk about friendly bisections and Boolean analysis. So take it away.
Thanks, Tor. So I'll be discussing on perfectly friendly bisections of GN1/2. And everything I'm discussing today is joint work with Tor, who's obviously in the audience, and Ashwin, who's a fellow graduate student at MIT. So I guess let me start by defining the object of interest. So a partition V in V into A1 union A2 of a graph V with vertices and edges is an H friendly bisection. If one, it's a bisection. So by this, I just mean the part sizes are as close as they can possibly be. And they sort of, it's a bisection, the union is everything and the intersection is nothing. And two, you have the property that every vertex V has more neighbors in its own part than in the other part, and H more neighbors where H is the same here. So maybe just pictorially, you have a partition A1, A2, and every vertex here has more neighbors in its own part than in the other part, and has H more. What? Sorry, yes. Yeah, so yeah, exactly. And this will also be convenient at some point if 2 holds for all but little o of V vertices. Call it an almost H-friendly bisection. So hopefully the definition is clear, and if at any point something's unclear, please do interrupt me. So I guess the motivating conjecture here was a conjecture of Ferretti. I don't think this is actually written down. I think he said he made it in 1988, but the way I learned this was this is in an open problems list by Ben Green. But it's like a collection of 100. It's a nice collection of 100 open problems. So if you sample G from GN1/2, then G with high probability has a 0 and almost 0 friendly bisection. And maybe as a brief comment, so if you remove the word bisection, you can sort of ask for this just to hold for any vertex, like for any partition, and not require that they're the same. Then this is obvious. You can just take sort of any, let's say just take the max cut of the graph or of the complement of the graph, the max bisection. Sorry. Okay, ignore that comment, but it's relatively easy without this word bisection. And okay, maybe as a heuristic of maybe why 0 is sensible, well, they're roughly something like 2 to the n bisections. Every vertex is a probability 1/2 of being okay with respect to any given partition. So if all these vertices were independent, then this is something reasonable. And so I guess last year in joint work, this was resolved. So this is Asa Ferber, Matthew Kwan, Bhargav Narayanan, and Ashwin. So myself, 2 years ago. So first, the conjecture is true. And furthermore, one can find a bisection with epsilon n violations in O epsilon n squared time. So the proof here is just algorithmic. There is some algorithm that does this, and it succeeds with high probability. So I guess the motivation for this talk is sort of, well, why are these two things here? So basically, so the question is sort of, A is the almost necessary. It's actually unclear what Ferretti conjectured here, but this is what was written in Ben's note. And B is 0 sharp. So I gave this sort of vague heuristic that every vertex is independent, but under the assumption that every vertex is independent, but is that sort of the sharp thing that's happening? So it turns out that neither of these are the case. And for this, I do actually just, I need to define some irrational constant, presumably irrational constant. I don't actually know how to prove that. So let gamma be the number which satisfies the following equation. I'm not going to motivate this, but just for concreteness. Just so that this is well defined. Z here is a mean 0, variance 1 Gaussian. So this is some constant, it exists. The main theorem is that this constant gives you the sharp answer. So theorem. So as before, G is sampled from Gn1/2 and fix any epsilon bigger than 0. So 1, G with high probability has a gamma minus epsilon times square root n bisection. And 2, G with high probability has no gamma plus epsilon bisection. So this is essentially a sharp answer to the question. A, you don't need any of these exceptional vertices, and B, gamma times square root n is just the sharp answer for understanding this property. Okay. The proof isn't written this way, but okay. So I guess, so the remark will sort of clarify this, but yes, you can remove that, but the proof is not written that way. I should remark that Dandy, Gomarnik, and Zdabarova sort of simultaneously, independently proved an analogous result. With almost and the same constant gamma times square root n. So that'll be a remark. And yeah, I might discuss the almost at the end. Okay. Okay. I guess so. I'll just start with. So I'll make some claims that are in the proof, and then I'll focus on one sort of aspect of the proof where sort of Boolean functions enters in. But to do that, let's maybe start with the proof of this theorem. So this is really a lie, but whatever. So what we're going to do is we're going to try to do maybe the first thing maybe you might believe might work, which is let's actually just try the first and second moment method here. Okay, so let x of gamma tilde be the number of bisections in Gn1/2. I'm sampling G from Gn1/2, which are gamma prime times root n friendly. So to prove the second part of the statement, we're just going to apply the first moment method. So, okay. So first, if gamma tilde is bigger than this threshold gamma plus epsilon, what we prove is that the expectation of x of gamma tilde, this is exponentially small. Once you have this claim, part 2 is just the first moment method. Okay. Fortunately, we're not so lucky for part 1. So for For below this threshold, well, okay, we're going to try to use the second moment method. And the proof sort of naturally, or the proof, if you do it the way we do, sort of loses a constant. You get something like this. And okay, so then given that the first and second moments match up to constants, something like the Paley-Zygmunt inequality implies the probability that, say, what we care about is z, this random variable being positive, let's say, that at least half of its expectation, you can check is bigger than 1. This is greater than or equal to some constant. But it's not, it's greater than some constant, but it's not with high probability. So if I wanted to prove that theorem just with constant probability, this moment computation suffices. Okay. I guess most of the rest of the talk will be sort of discussing how to remove this condition, but maybe briefly. So these quantities are, so this is not some obvious computation, and maybe a brief bit why. So these quantities naturally live on some exponential scale. So I'm saying that I can look at a graph and sort of, just for the expectation, there's some exponentially small probability that a given partition will be a friendly bisection. And I'm telling you that then I can estimate this probability to within, let's say, at least a constant factor. Naively, this seems like a relatively hard task, maybe even a little bit hopeless, but it turns out that there are ways to maybe think about this. The sort of key insight, maybe the starting point for all these computations, is that the condition of a bipartition being friendly is only a function of the degree sequence. So in particular, I can look at every vertex on each side and sort of look at their degree into this part and to the other part. I can record that information and just count the number of graphs of that form. Amazingly, we have tools for this. So there's quite nice work of McKay and Wormald. I think this is from '88, but which essentially tells you how to count such things. It's based on complex analysis. After that, there's still quite a lot of work. You sort of need to see this magical constant. This comes out of comparing this with a certain Gaussian model and realizing that the computation is exactly the same. And then you need to figure out some way to enumerate over all such degree sequences. And that's a large part of the technical work. So this gives you the expectation. The expectation squared is something similar. It's 2 partitions. But after this point, there's still quite a lot of work, but I don't want to focus on that for the rest of the talk. And maybe a brief remark. It won't be true in general that something like a first and second moment method will actually capture the truth of the threshold here. So this is kind of a very special thing that's happening. It's happening due to sort of how, sort of, if you look at the set of bisections which are valid for a given graph G, they sort of form a very nice subset. In particular, they're kind of well separated and all the way up to the threshold. And this sort of is what plausibly makes it possible to apply the second moment method.
The second moment method, do you count the degrees into each of the 4 parts, or?
Yes. Yeah, and then you need to then enumerate over it. So somehow there are really like 10 parts of this graph, or 11. So, I guess there was also, yeah. Okay. So I guess, and also I erased this, but the first and second moment don't match up to constants. There's some numerical constant that comes out of the proof. In reality, if you think about it pretty hard on what's happening with the physics of the model, almost certainly these things actually don't match up to a constant. There should be a constant factor deviation. Either figure out how to remove that. There might be ways to do this. Or you can try to just like bootstrap a result for free. And well, there's one nice way to do this, which is try to use Boolean functions and sort of remove this. So there are many theorems of this form, something like Friedrichs-Hunter theorem or from Benjamin Klein-Schramm on percolation, but it's not, so there's no varying P here. It's not immediately clear how Boolean functions will enter the picture, but that's sort of the upshot here. So maybe let's just try some naive concentration attempt first and sort of see where we get. So for the rest of the talk, I'm sort of going to think of GN1/2 as just a random subset of 0, 1, a random string in 0, 1 to the n choose 2 by identifying edges with n choose 2. And so we know that, let's say, the measure of f is greater than 1, where f corresponds to graphs which have a friendly bisection. This is just an equivalent way of writing the conclusion of the second moment method on the other board. So given this, I mean, let's maybe consider, if we're going to view this as a subset of the hypercube, let's consider the most natural distance. So dist here is just the Hamming distance on the hypercube. I'm going to sample a graph G from GN1/2. And I'm going to look at the distance of G from this family F. So what is it typically? Well, okay, so this is, it turns out just to be bounded by something like n. This is just because the probability that this distance is 0, this is greater than some constant. And then you can either use vertex-isoperimetry or something like Azuma-Hopting to show an inequality like this. This also already gives you something pretty non-trivial. So you can find a bisection missing at most with, say, something like square root and bad vertices. Where by bad vertices, I mean vertices which violate being a friendly bisection. This is just because in order to make a single vertex bad, you sort of need to change square root n edges at that vertex. And if you're only moving by distance n, you can only make this many bad. And this is a pretty non-trivial thing. This is why almost is somehow much easier. It's because you have these like strong concentration measure tools, which are available to you. But if we want to get exactly friendly, we'll need to do something more. And the main thing is we sort of forgotten maybe the key fact about this family and what we're aiming for. So somehow the Hamming metric is maybe not the right metric here. We don't really care about the number of edges you change. We do care about how these edges that you change are distributed throughout the graph. So that's the first thing. The rest of the talk will be sort of discussing this. So for this, I'm going to define the dist between two graphs. I apologize in advance for bad notation, but so this is the max degree. And I look at my two graphs and I look at the symmetric difference between them. So these are graphs. I look at the symmetric difference. I look at the max degree. The reason this is maybe the right metric, if you care about this problem, is that sort of if this distance is small, and let's say G has an H-friendly bisection, then has an S-friendly bisection, then H has a S minus 2T friendly bisection. So somehow this metric is capturing exactly the notion you want to know. You just want to know how many vertices that change at a given edge. And the main theorem is sort of all you need about F for our result is that F is a symmetric family. Because the property of a graph having a friendly bisection is obviously symmetric under permuting its vertices. It turns out that's all you need. So let me just take the theorem formally. Suppose you have F, which is a subset of 0, 1 to n choose 2. That is Sn invariant. And the measure of F is bigger than epsilon. Then probability that dist tilde of G from the family F. So here I just mean the minimum distance is something in the large family, where I sample G from Gn1/2. That this is greater than a C log 1/epsilon square root n over log n. This is less than epsilon. And so this immediately proves the result we want, because take epsilon tending to 0 slowly, square root n over log n times some slowly growing function is still little o of square root n, and we have gamma times square root of n root. So given this, the result is proven, assuming that you believe this computation. Just one remark before going on. Also, now is a good time for questions. This statement is sharp in epsilon and like the 1 over square root log dependence. And it comes from a rather natural example. What you do is you consider the set of graphs which have atypically high maximum degree. Roughly having maximum degree, like you look at the median maximum degree, having maximum degree this much higher occurs with probability epsilon. And to change the max degree, you need to change the edges at that vertex. So somehow this suggests that you have something that looks like a dictator, something like a dictator type thing. So maybe that suggests that Boolean function should be relevant. Okay. Yeah, so I guess for the rest of the talk, the goal is to just prove that theorem. So are there any questions?
Is there like an approximate value?
I think it's like 0.71. You can compute it to basically arbitrary position.
Okay.
There's an easy fixed point procedure that gives it to like however many decimal places you want. What?
It's smaller.
Yeah. Okay, so I guess now I'm just going to recall a bunch of Boolean function definitions. I'm just going to keep them on this board so that I have access to the rest of the talk. So as a standard, you define the influence of the ith coordinate to be the probability that switching the value of the ith coordinate sort of switching the ith value of the coordinate changes the value. The total influence is just the sum of all these influences over, you sum over all the coordinates. What is the influence? Also need the notion of sort of the positive sensitivity. So I have a point X in the hypercube. The positive sensitivity is just the sensitivity given that the point is not in the set. So, or you can think of functions that obviously sets. They're 0, 1 value to sets. finally, the main result we'll need is a quantity relating sort of the positive sensitivity to the influence and the variance of the function f. So this is a theorem of Eldon and Gross. There was a simpler proof given by Eldon, Kindler, Schutz, Minzer. What we need is that the square root of this sensitivity, the expected value of this is at least sort of the variance of f. So this is a natural quantity because somehow like this is telling you the number of coordinates you can change, sort of like this tells you probably kind of click change, but you pick up some factor based on the total or the sum of the squares of the influences. Square root of log of 1 plus 1 over sum of. This goes under another name. There's a constant hiding here. Oh, an absolute constant. So unfortunately, the first step of this proof is a little bit uninspiring. The first step is to sort of get yourself into, you want to derive some combinatorial decomposition using this on like functions which are symmetric. I'm just going to state the lemma and maybe give the proof. Short. I'm going to fix epsilon in 0 to 1/2 and let the expectation of f and f is Sn invariant. So one of the following three scenarios occurs. Either you have that with decent probability over the cube that that at a given vertex that you can sort of, there's a coordinate you can switch so that you're okay. So the correct threshold turns out to be epsilon log n over n. 2 and 3 will look very similar. What it will say is that instead of just trying to look at the probability that you have large positive sensitivity, you're going to you're sort of going to try to balance this probability against the number of large coordinates you have, against the number of vertices that have that many positive influence, that many positive changes appropriately. So more precisely, there is j such that 2 to the j times the probability that SF plus of x is in 2 to the j to 2 to the j plus 1. This is bigger than, oh, I'm also going to lose like log factors over the result I promised, but I'm not removing those is just a little more cleverness with this decomposition. Finally, there exists j such that one, it lies in some specific interval, which will be relevant later. And 2 to the j over 2 times the probability that SF plus is in 2 to the j to 2 to the j plus 1. This is greater than or equal to epsilon times square root log over log. Sorry, that's not a probability, it's some number. And the proof of this is just like these two quantities basically tell you the sensitivity and the square root of sensitivity, and we're just going to derive some inequalities based on that. So nothing particularly deep is going to happen at this point. So the total influence is just the sum for j bigger than 0 to 2 to the j times the probability that positive influence is between 2 to the j and 2 to the j plus 1. So there are a couple of cases. So one, if I of f is bigger than, let's say something like n to the 1/2 times some like large fact, get rid of 100 there, okay. 102. Suppose this is pretty large. There are some dyadic buckets in which you're okay. Great. So this case, check mark. Bad practice, I'm now going to just reverse the inequality sign. So we can assume that for the rest of the proof. So this gives you something. I need to use this inequality, so I'm going to now bound the sum of the influences squared. This is the one place symmetry comes in. Because we know it's symmetric, we know that all the influences square, all these influences are the same. This is just the total influence divided by n choose 2. And if you plug this in this is less than n to the minus 1/2, say. So in particular, this lets you derive that the expectation of the square root of the sensitivity, this is at least epsilon times square root of log n. That's just using the theorem of Eldon and Grosser, the other authors. Okay, we can also now assume that the first condition doesn't occur. Otherwise, kind of by definition, we're done. So SF plus is greater than 0. Well, this is less than or equal to epsilon square root log n. Now, the last part is you just write out what this expression is. So this is the sum. For convenience, I'm just going to let this be w of j. So it's 2 to the minus j over 2 times w of j. So we know this is literally the square root of the sensitivity up to a constant. So this is bigger than epsilon times square root of log n. And so I have to sum over 2 to the j, which goes between like 1 and the number of coordinates, which is like n choose 2. So first, where are we going to use this condition that the probability of having a coordinate which you can switch is small? Well, this just tells you that the small terms in this sum don't contribute very much. So this is basically equivalent to, you can kick out terms which are less than, let's say, n. So we've eliminated that much. The second half is that, well, we know that the total influence is bounded by n to the 1/2 times some log power. Well, okay, anything bigger than n times some large power of log, this 2 to the minus j over 2 is something like root n. So root n times this, if you choose like, you make the 2 to the j between n times log n to the million, log into some large power, then this is also approximately the same as like the sum of I might have lied on the constants, but whatever. And now there are just log pieces in the static sum. One of them will satisfy the bottom. I think I even can put this. But okay, great. So is that clear? Okay. So given this, we're going to sort of do some we're going to try to prove the main theorem sort of by bootstrapping off this there's some combinatorial bootstrap off this fact, which will give us the final result. I will now proceed to erase the board I just wrote, which, well, I need 2 boards.
Top line 1, 2, or 3 holds.
Yeah, sorry. Oh,
I think you said it, but didn't write it.
yeah. Thank you. Thanks. Yeah.
Split the case based on which one of these holds.
So okay, let's maybe let's pause here for a second. So somehow I need to show this fact that like I have some family which is a set size epsilon. I need to show that somehow there's some like small, maybe bounded, like small in degree perturbation of it, which sort of gets me to this family, typically. So what I'm going to try to do is sort of use these cases to sort of grow my family slowly to some larger set. And then once I've grown it, I want to then verify that through this growing procedure, I can sort of find a certificate in the original set, which shows that I'm still close in maximum degree. It requires the proof requires a little bit of work, but okay, let's maybe start along the path. The issue, sort of the setup will make it clear what the finish is. So we consider a set of expansions of our family. So just for concreteness, so F0 will start off at a family F0, which is just going to be equal to F, and Fj will be the J family. K will be the Kth family. So I'll think of like capital F as a subset of like 0, 1 to the n choose 2. And all of these will be families of graphs, so they'll be S invariant. Also, just so I can cite the indicator facts, so like little fk will just be the indicator of capital Fk. And by assumption, we're going to look at mu of F0, which is going to be epsilon. And what I'm going to try to do is grow from epsilon to 2 epsilon, and that's enough. You just repeat like log 1 over epsilon times, you double, you're done. So that's all I'm going to do. So we're not going to have too much control on the family Fk. So we're just going to try to expand using one of these conditions. So there's going to be algorithm 1, which said, or a step 1, maybe an algorithm 1. So if the probability of Sfj plus is greater than 0, is greater than epsilon times square root of log n over root n, then I'm just going to define Fj to be Fj minus 1 union the points which satisfy this condition. X such that Sf plus of x is greater than 0. So that's step 1. That's the first algorithm. The second algorithm will be, move it over, it'll be 2j. So there is a j such that 2 to the j times the probability that Sf plus is in 2 to the j to 2 to the j plus 1. And this is bigger than this like funny threshold I wrote earlier. Then I'm just then you just define Fj in the obvious way. Once again, you just take the points x which exhibit this. Okay, sorry. Great. Okay. Now I think F and J's are hopefully distinguishable, or F and K's are hopefully distinguishable. Plus is in and okay. Log 3j, the same thing. So you have your family at this step. You look at its corresponding function. You look at the corresponding function. You know one of these 3 applies. Find one of them that applies and sort of expand the family using the definition. Okay. Okay. And as stated, this algorithm goes on forever. I'm just going to define a termination condition. Terminate when the measure of mu of fk is greater than 2 epsilon. So naively, I don't really have any sort of control on how long this algorithm runs, but the thing we're going to prove is the obvious thing. At the end, every graph in fk, I'm using notation here, every graph here is in this distance tilde metric, square root n log n from some graph in the original. If you have that, you're done. Okay, so let's try to at least get some control on this algorithm. The way we're going to get control is we're just going to say, okay, how many times can you do each of these steps? That's maybe the first step. Alg1. Well, how many times can this run? Well, every time if this is true, the measure of the family went up by epsilon square root log n over n, and I'm trying to go to 2 epsilon. So there are at most square root n over log n such steps. We're also just going to use the same bound for these 2 steps. So how many times can we run the second step? Well, now we know that, well, the measure doesn't go up by epsilon times square root n, that's bigger than 1, presumably, but it goes up by at least 2 to the minus j times epsilon times square root n times log n to 100. So it turns out there are at most 2 to the j over square root n times log n 100 steps. Of 3j. Okay. Now it's helpful that I at least have this written here. So there are at most 2 to the j over 2 times log n squared over square root log n steps. Once again, these 2 facts are just because every time you apply this step, you know that the measure goes up by so much, and we're just trying to get to 2 epsilon. So now I have to, so now I've done this whole setup, and I've written things down with SF plus. I do actually need to use this somewhere. And the key point here is going to be that you can balance sort of, if 2 to the j is very large, like let's say n squared, I mean, this is n to the 3/2 steps. So n to the 3/2 steps means you could completely destroy a vertex. So you need to use something about SF plus. What you're going to ultimately use is that you know that you have many choices. And for this, well, I'm now going to draw a picture that looks very backwards. So I need some notation for the stopping time of this process, like the last time. That's just going to be tau. I'm now going to draw it extremely backwards for some reason. So I just want to show that every point in SF tau is somehow close to some point in every point in F tau is somehow close to some point in F0 in this metric dist tilde. Let's assume, basically without loss of generality, that so notice that at every step we're sort of keeping the old family and just sort of increasing it. Let's pretend that we know that the graph G that we care about gets added at the last step. I'm not really assuming anything here. Okay. So somehow I want to look at the path and the history of how it got added, right? Notice that every time you get added, there is a graph in the previous family. You're either the same as some graph in the previous family, or there's a graph in the previous family which is somehow close to you. In particular, you've changed exactly one edge. Okay. So what I'm going to do is I'm going to construct a path, but going backwards. And these two facts, plus that we know that SF plus is sufficiently large, will be enough. So let's maybe do this. So at every step, there's some like label for the step. It's like an alg1 step, or like an alg2j step, or let's say an alg3j step. So I'm just going to sort of bound the max, like the number of changes sort of, and the change to the max degree that happens from each of these steps separately. So alg1 only happens n over log n times. So this doesn't change the max degree. Doesn't cause enough change. Now let's look at alg2 to the j step. So what do I mean by look at a step? So I'm going to construct sort of what I'm going to do is I'm going to sort of construct a history of edges going backwards that are sufficient to change to get from here to the final thing. And that like history of changed edges will be sufficient. So at some point, I have an alg2 to the j step. So there are at most say 2 to the j over square root n times log n to the 100 such edges that I've changed earlier. This is just because that's the total number of steps. So how many of these have high degree? So there are less than or equal to 2 to the j. So this is like, look at the graph induced by the change. You've constructed a history so far. Look at the set of edges you've changed due to alg2j. How many vertices in that auxiliary graph have degree above square root n times log n? There are at most 2 to the j divided by n times log n to the 100 high degree vertices in this graph. So this is the complete graph. If you have a set of vertices, the number of edges possibly emanating out of there is like 2 to the j divided by log n to the 100. Bad edges you can't add. And now we're done, at least for this step. Because at this point, if you got added an alg2j step, you know that your SF plus is between 2 to the j and 2 to the j plus 1. So there are a bunch of bad edges which correspond potentially to high degree vertices, but it's okay. You have enough choices. And I'll also verify this for the final step. So X, to sort of continue this history backwards. So I want to construct a certificate of edges that I can change going backwards so that if I look at the set of edges which have correspond to like alg2j steps, at every step, that graph has bounded maximum degree, like has bounded degree. The point here is what I'm saying is that, okay, look at the number of vertices in this graph which have high degree above root n. There are very few of them. Because of this, there are very few bad choices for me. There's at most the number of high degree vertices times n. But I know that since this came from this step, SF plus is large. It's larger than 2j. So I have some way of continuing this history backwards. That's enough. And for alg3j, it's similar. I'll just do the computation. So there are at most this many steps. So number of vertices of high degree. This divided by root n. So it's less than or equal to 2 to the j over 2 over root n log n, some like log logs or something. And so, yeah, so how many changes do I have? I know that I have at least 2 to the j changes, like possible changes. And I'm going to multiply the number of bad, like possible choices, like 2 to the j over 2 times root n divided by like log n. So, and if you rearrange this is like, certainly if 2 to the j is bigger than n, this is fine. And we guaranteed this here. So you can always just construct this history backwards. So instead of looking forwards, you look backwards, and that's enough. And with that, I mean, that's the full proof. I mean, I slightly lied. You need to maintain that, like, you can sum the degrees, but I have lots of room. Like, I have like logs of room here, and there's only log n such graphs here, so it's fine. Okay. Are there any questions? If not, I'll just leave with like maybe one open problem, which I think is quite interesting here.
So first you do, like for the bisection problem, the second moment to get that the measure is epsilon, then you apply this theorem.
Yeah, you get that it's a constant, then you just apply this theorem. Yeah, exactly. And maybe just as an open question that I think is actually quite interesting. So can one find algorithmically a 10 to the minus 10 square root n friendly bisection with high probability? If you want, I'm willing to put an almost there. It's not clear how to do this because this proof is purely existential. But with that, that's all I had to say.
Is this related to Talleyrand's inequality and anything?
Yes, I mean, so this, yeah, this is the Talleyrand inequality. This was his conjecture, and it's just yeah. And this is the resolution of Talleyrand's conjecture. Yeah.
No, but there's a general Talleyrand inequality where you have a set which is not super small and you slightly expand it, and then it's almost everything.
I mean, like stronger than isoperimetry?
No, this is a general thing with you. What's known as Talleyrand inequality? Because there are several things
Like this?
No.
I
There are
think
many
he's
things
talking
called
about
Talleyrand
Yeah.
inequality.
the initial isoperimetric thing that you did. That like if you have a large family, then anything is close to it up to root n, but your n was n squared, so it was n.
Oh, sorry. Yes. Oh, isn't
So this is the thing that he started with.
I mean this is vertex isoperimetry on the hypercube? Okay.
So it's like an improvement of this.
Yes. Yeah. And so the point is the Hamming metric is the wrong metric for at least this problem.
Yes.
Is it accepted GMP?
For p constant, yes. For p like little one, so the almost thing is still true. Don't quote me on this, but I think the first and second moments probably start to differ by more. It's extremely unclear, actually, to me what I suspect it's true. So a lot of this, right? A lot of this gets harder, and that part also. The first and second moments, it's not actually clear. Like I think you start losing factors in p. Yeah, it's not at all clear.
Is the threshold the same for different peers?
So it's the same. It's the same in the sense that what you should do is you should renormalize. You should do like gamma times square root n times like p times 1 minus b times 2. This would be the thing in general. At least for constant p, this follows almost immediately from the proof. But for smaller p, it's very unclear. It breaks at some point, obviously, but I think basically as long as the question makes sense, it should be true.
So there's another technique in random graph theory to handle these things where the variance is too large or you condition on something.
Yes. So I don't want to discuss this, but so the reason, so what you do is this is generally applied in small, like sparse graphs. It's called small subgraph condition. You're going to apply you would, let's say, at least need to know how to prove a central limit theorem for small graphs and degree constrained random graphs. That's not easy / obvious.
No, but maybe you can do the opposite. Maybe we can use this kind of concentration to.
I mean, so Friedrich's theorem like serves that purpose in a lot of applications, right? Like in sparse graphs, you often use Friedrich to just remove the small subgraph conditioning. In some sense, this is like a dense analog, the right dense analog here for us. I think that answered your question. Was it more precise?
I think there's different regimes. This results are in the sparse regime, and this is the.
Yeah. So it turns out. Almost certainly the like cause for these like deviations are similar deviations in small subgraphs, it turns out. There are related models where this is shown by Sly and co-authors, the symmetric perceptron model. And there you can use some version of small subgraph conditioning, but they use very strongly that they're in Gaussians. It's very hard to do that. It's extremely unclear how to do this for degree constrained random graphs. It's probably also very painful.
Okay, if there are no more questions, let's thank Mehtaab again. And we'll meet in 30 minutes for the last talk.